One of the things I really want to talk about is some of these questions where there were obviously some challenging with the answers. So this one, and in this quiz I really picked answers that are ones that I've tended to get in the past that are wrong. So here is one that's wrong. So this refers to Spider-Man trying to stop the train, putting his feet on the tracks and the track breaking apart. And what he said, what this one says is his momentum, or the momentum of him in the train, is too great. So the tracks cannot make a large enough force to equal the large momentum. So what is potentially wrong with this sentence? Yes?
Wouldn't the forces be equal?
Okay, which forces?
The force between, I guess, his feet and the track.
So there's definitely the sense that the force between his feet and the track are equal. So that force is equal. What else is wrong? Though that doesn't necessarily come into this sentence. It would suggest that there's something wrong here, but that's more, to be honest, for the later one here, that's also wrong. So that's more directly relevant to that. What's really the problem here? Yes?
Force and momentum aren't the same thing.
Force and momentum are not the same thing. And this is a very key idea. This is one of the most important ones that causes the most confusion and people use incorrectly. So if I want to talk about momentum, what is momentum?
Mass times velocity.
Okay, so the idea is it's mass times velocity. That's its formula. But one thing to keep in mind, it's a property of an object, or sometimes we'll talk about a whole system and its momentum. So it's a property of something, and that's a key word right there. And it tells us how hard it is to change the object's motion. And that's why we get the formula mass times velocity. And the reason is, if you think about the things that make it hard to change your motion, if you are more massive than another object, it's harder to make you move or stop moving. And the faster you move, the harder it is to change the direction you're moving or what you're doing. So these are the two things that make motion hard to change. And so they're the key ideas behind momentum. Now, what is the main thing about force? What is a force? Fundamentally. When do you get a force? When you push or pull. So what has to be there for a force to occur? How many objects? Two. And they have to interact. A force is fundamentally an interaction between two objects. So notice the difference. And this is an important thing in science and physics when we're trying to describe stuff. We want to distinguish between the properties that objects and systems have and the ways they interact. And the forces tell us about the interaction. Momentum is one of those things that's a property of a system. What are some other properties of a system? List some other things that are properties that a system can have.
Changing form?
Well, that's something it might do. It might change its form. So, but what's a property that it could have? Its state or its form would be a property, right? Changing it is something that happens to it. And we're going to come to that more in phase transitions and stuff in the next weeks. But what's some other properties that you might, where are you right now?
Location.
Yeah, so your position is a property you have. It's where you are. What else might you have? You might have acceleration. And let's put that down here because what is acceleration? a change in velocity, so you might also have a velocity. We already listed momentum over there. What's another big property of systems and objects that describes their state? Energy is the other big one. These are the main ones we'll talk about. And energy, there's just a whole bunch. And I'm not going to list them here. But what are other things besides forces? So forces are interactions between objects. And forces change what? When you have a force, what is the connection between force and momentum? Well, what's the famous formula for force? F equals what? F equals ma. Whose law is that? Newton's law. Which one? His first, second, or third? One of the three. This would be the second one. So if you want to look cool and memorize one physics formula, you should memorize this one and E equals mc squared. And then you've got Newton and Einstein, the two big guys, and you're good. Okay? This is the way the form's generally written. What's more useful is to keep in mind that forces cause changes in momentum. And since momentum has velocity, and usually your mass stays the same, this is usually a change in velocity. And a change in velocity is an acceleration. And that's why we get the formula force equals mass times acceleration. What you want to keep track of from the content part of the course is when there's a change versus the thing itself. So force is an interaction. It causes a change in momentum. It doesn't cause momentum, and it's not the same as momentum, and it's not related to momentum. So in this quiz question, when we say the force is not equal to the large momentum, that's just a sentence we cannot write in physics. We are not going to equate forces and momentum. We need to equate forces to changes in momentum. And then that's a sentence that would make sense. Does that help? Questions? How does that feel? We better about that? The other big one, well, this one had a few people. The energy of the train in Spider-Man is conserved because the train is so much more massive than the wood. This is, again, one of those sentences that just from a physics point of view makes no sense. There's a lot of things in here that are not connected. Energy of the train in Spider-Man being conserved, well, those are only conserved if there's no other interactions that can make the energy go anywhere. In fact, in this case, what's actually happening? If I have Spider-Man and the train here with some energy, and Spider-Man is interacting with the tracks here, which are braking, what am I going to say about energy in this situation? What words would I use? Where are there various different energies? Tell me some of the energies that are going on. Does Spider-Man and the train have energy? Yeah, what energy? They're kinetic, but close. Yeah, kinematics is the description of motion. Kinetic is the energy of motion. So it's their energy of motion. And what's happening to the tracks when they break? Is that a sort of energy? Well, when something breaks, what energy is involved? Does it take energy to break something? Let me put it that way. Sure, because what have you broken? At the molecular level, what are you breaking? What sort of things? Chemical bonds, and that represents a transfer of energy. So energy goes into breaking them. Once they break, what do they tend to do? Fly away, so that's what type of energy? Kinetic energy. right? So what's really happening is the energy from here is going here. And if I think of all of this together, now I can say the energy is conserved because there's nothing else interacting with this. So energy is something we want to keep track of, and depending what we pick as our system, it's either moving from our system to another system, or it's conserved because it's all staying within our system. Does that help a little bit? The final piece here we already talked about. The force of the train is bigger and so on. You already addressed because they have equal and opposite force, because they're just interacting with each other. So why do the tracks break if there's equal and opposite force? Right, so I have Spider-Man here, the tracks here. We have this single interaction, which is one force. It's the same on both. So why do the tracks break?
Is it because of mass?
Could be because of mass, right? Because they have different masses, they get different accelerations. In this case, it's probably more just the material properties. Spider-Man's bones are stronger than the tracks. So it's a big force, it breaks the tracks, but not his bones. That's fundamentally, do any of you do any sort of karate and break wood or bricks? But if you did, the reason the wood breaks and not your hand is because your bone is actually stronger than most wood. It also turns out other features come in. The forces are the same, but how the force is distributed can be very different. Your hand is very fleshy, so the force spreads out along it. The wood has a structure that tends to concentrate forces, and so it makes breaking points. So it's the impact of the force can be different, but the force itself is the same. And we're used to seeing the impact and thinking about that. And so we sometimes get confused and think there's two different forces when there's one force but two different effects. Where would mass really come in? When you're noticing accelerations. Like if two people collide and one bounces off and goes flying and the other one stands there, it's usually the more massive one that doesn't move, right? And again, that's this. They had the same force, but the more massive one had a very small acceleration, and the less massive one had a big acceleration. The other question I wanted to point out, people were pretty good with the energy of the train. These are all energies that are in there. And so you just have to be careful and recognize that they're all there. Most people recognize that Spider-Man's webs, anything stretching is usually elastic energy. The one thing you have to be careful about, we do talk about in physics the difference between an elastically stretched thing and a plastic stretched thing. If it's plastic, it doesn't come back. If it's elastic, it stretches and bounces back. So the webs are elastic because they bounce back. And this one, I just wanted to make a quick comment. I was a little surprised. From a physics point of view, ripping the bricks out of the wall, it's not hard to explain. The force from the webs is bigger than the force holding the bricks, and so the bricks come out. So I don't know what, if there was a particular question you had with that you thought that was a difficult one to explain with physics, please let me know. But that's kind of where we were thinking of it. Any questions? Excellent. Okay, well, so we'll stop with that.
Why is that the answer?
Why is Spider-Man's suit ripping? Because there's really no reason for his suit to rip just because he's using his muscles. It's not like they suddenly got bigger on him. Yeah, not real. I mean, just when you lift and move stuff, I mean, your muscles expand a little bit, but presumably you're smart enough to wear a suit that's stretchy enough that it's not going to rip your suit. And that's where the physics fails. Yeah. No, one thing, it is certainly true that from a movie point of view, if I want to prove that you're super strong, I rip your clothes. I mean, that's like the standard thing. Okay.